Good morning everybody. Today I am going to tell you about the systems which have congruent melting point. So as we have already seen that the two component systems are of two types. One in which the two components they mix freely with each other and but they do not react with each other. And another one is in which the two components they react with each other, and these further are further divided into two types. These the systems in which the two components react with each other, they are further divided into two types. One in which the compound formed after reaction it has congruent melting point, and the other one in which it has incongruent melting point. So first of all I will tell you what is actually the congruent melting points. When the two components which react with each other they are stable up to their melting point, then we say that they have we say they have congruent melting point. So today I will tell you about an introduction of the phase diagram of such two component systems which have congruent melting points. Means the compound form does not decompose before their melting point and it is stable up to their melting point. So let's consider a compound A and compound. Let there be two components, component A and component B. Now I have you are already familiar with all these graphs. This is the temperature axis. This is the temperature axis. This is again the temperature axis for the component B, where we will depict the freezing point of the pure component, and here we are having the pure component A, 100% of A, and here we are having 100% of B. Now suppose we take a vessel and we are studying the heating and then the cooling, the separation of the compound of the components A and B at atmospheric pressure. And since we are studying at atmospheric pressure, and since it is a solid liquid equilibrium, the vapor phase is almost neglected, and so we ignore the pressure variable, and it is a condensed system. As I have told you earlier, it is a condensed system, and we will apply the reduced phase rule equation in all the various parts of the systems, like the curves, areas and all. So let us consider, let us take a vessel in which we take component A. Let us take 90% of component A and we have 10% of component B. Now suppose, and we heat it to a temperature above the freezing point of A and B, and let this be the freezing point of A and let this be the freezing point of B, somewhat higher than A. So we will heat it to a temperature, and suppose this is 90% of A and 10% of B is added to it, and let it be heated to this temperature. This temperature is above the freezing point, or we can say above the melting point of both A and B. And when we heat it to this temperature, what will happen? We will get a liquid melt. Since A and B are miscible in each other, they will get mixed with each other, and we will have a liquid melt of A and B. So what will happen? This is the liquid melt of A and B. Now we will start cooling it. We will start cooling, and when we will cool it, we bring the temperature down. Then what will happen? Suppose this is the freezing point curve of A, to which different proportions of B are dependent. So what will happen? It will cool to this point. Let it be P. It will cool, when it will cool to this point, to this temperature. When it is cooled to this temperature, then A will start separating out. This is what we have been studying for previous components also. that when we will mix in this proportion, then a point will come when solid A will start separating. Solid A will separate and the remaining mixture will be rich, somewhat rich in B, because A is getting separated out. No, here A is getting separated out. Then what will happen to this melt? It will become a bit rich in B. Now the composition of B is somewhat more than that of the previous one. So what will happen? The composition is, suppose the composition is now this much. Suppose the composition is this much, then it will again, now the freezing point is again depressed. Okay, since the component B is more now, since A is being removed, this is A is being removed, so this is rich in B now. The composition is now changed. It will be no where the 90 and 10. It will be somewhat. If we talk about the concentration of each one, then this will remain the same 90%. Somewhat, suppose 10 grams of it is solidified, then this will be less than this 90, and this 10% B will be more now when we see the collective concentration. Okay, suppose you are having 10 oranges and you are having 10 bananas, then you will say that you are having 50 and 50%. But if you eat 3 bananas, then what will remain over there? 7 bananas will be remaining and rest will be apples. So apples have not decreased, but if we talk about the relative proportion, then obviously the relative proportion of apples will be more than that of the banana. Okay. So the same thing happens over here also. This A gets solidified, so this melt becomes rich in B. The composition is shifted to this side. Now the melting point is again depressed, decreases. The melting point of A decreases with addition of B to it. Now what will happen? The composition will again change. But what will happen at a certain point? We will find that A is already solidifying, but along with A compound AB is also solidifying. A compound AB also starts solidification. Not B, but only AB and A. Along with A compound AB will also start to solidify with the decrease in temperature. And let this point be C. Okay. Now at this point, what will happen? We will be having solid A. Okay. We will having the liquid melt of A and B as well as this compound AB. This means 3 phases are present at this point C. And if we calculate the degree of freedom from the reduced phase rule equation, it will come out to be 0. Since there are 3 phases present and it's a 2-component system, so the degree of freedom will come out to be 0. So this will be one of the U technique point. Okay. Now just consider, suppose this is the freezing point of pure component B, and we add varying proportions of A. Similarly, the freezing point of this will also decline. The freezing point of this will also decline, and with the addition of more and more of A in a similar way. Now we will take another vessel in which we are taking B along with, to which A is being added to it, and when A is being added to it and we heat it to a temperature above the freezing point of both A and B, we will be having a homogeneous mixture of A and B, the liquid melt, and when we will cool it down, then what will happen? A point will come when solid B will again start separating out, and the composition of that liquid melt will change because B is separating out, A is over there, so the proportion of A will start increasing in that melt. finally what will happen? The freezing point will decrease in this way with more and more cooling, with more and more separation of heat. Now a point will come when the A and B will not separate, but a compound formed by A and B, let it be AB, the compound formed will start separating. अब सिर्फ B ही सेपरेट नहीं होगा, जैसे हमने यहाँ पर देखा, सिर्फ A ही सेपरेट नहीं होगा, A ही सॉलिडिफाई नहीं होगा, कंपाउंड AB जो कि A और B के रिएक्शन के कारण बना है, वो भी सेपरेट होना शुरू हो जाता है. So a point will come when AB will start separating. Let this point be D. At this point, what will happen? How many phases will be there? There will be one solid phase of this component B, which is this side, and a solid phase of the compound formed due to the reaction between A and B. A and B में अभिक्रिया के कारण जो कंपाउंड फॉर्म हुआ AB, वो भी यहाँ पर मौजूद होगा. B हो गया, AB हो गया, और एक लिक्विड मेल्ट का फेज यहाँ पर होगा जो AB का लिक्विड मेल्ट था. So again you will see over here, just as we have seen at point C, that there are three phases in equilibrium, and since it is a reduced phase rule equation will be applied to it, so again the system will be non-variant at this point. So we see that this is one Newton point and this one is the another Newton point. So the graph, it comes out somewhat like this. This I am showing only for your easy understanding. I will again tell you all the graphs and all the curves when I will tell you about the zinc and magnesium system, which follows this type of phase diagram. So this is somewhat like this, and when suppose we are taking a proportion, let it be suppose let it be 40% of A and let it be 60% of B. Let's suppose we are taking a composition of 40% of A and 60% of B, and this corresponds to the peak of this graph. So if we take any composition over here, so here we are having the liquid melt of A and B. We are having the liquid melt of A and B. Okay, plus A plus B. We are having the liquid melt of A plus B over here. So when we decrease the temperature at this point, what will happen? It will be lowered to this temperature, this particular temperature, and what will happen at this point? A new compound which is being formed, AB, that will solidify. The new compound formed will solidify below this point. So what we have above this point, we are having, now if we heat it, we will have a liquid melt of the same composition as that of the solid. This means that we are having this as the congruent melting point of A and B. This is the congruent melting point, means at this point we are having two phases. One is the liquid of AB, same composition. We are having the phase of same composition, liquid AB, and one is the solid AB. At this point, when we lower the temperature beyond this point, what will happen? We will get a solid, AB will separate out. And if we heat it, we will get a liquid of the same composition, AB. We will get liquid AB and we will get solid. So this is actually, there will be two phases of liquid AB and solid AB. Okay? So there will be two phases, liquid AB and solid AB. Now, so this is a typical phase diagram for a congruent melting point system, and a typical representative example of which is the the magnesium zinc system. So this you can see the phase diagram is constructed in this way. These are the two eutectic points, and this one is the congruent melting point. Okay. So this is all about introduction to the phase diagram of a two component system which has a congruent melting point. The basic feature of it is that it has a point at which we have two phases, the liquid compound which is formed by the reaction of component A and component B, and the solid compound A and B. They have the same composition, they will be having the same composition, but the phases are different. So this is all about a two component system. Two component system with congruent melting point. Hope you all have understood it. So this was all about that, and you will understand more about it when you will study the zinc magnesium system. Okay, thank you so much.